Okay, for part 2 here for section 3.4, we're going to look at another example of an application problem dealing with derivatives, and that is going to be what we call marginal cost. So we're going to start out with a cost function. If you look at number 10 in your book, this is the cost of producing X amount of washing machines. It's variable, of course. It's got a quadratic equation as part of it. If we were to graph the quadratic, it would be upside down, of course. And what it generally means is that depending on how many washing machines we produce, it's going to cost us a certain amount of money. So, for instance, if we produce 0 washing machines, it's going to be an upfront cost of $2,000. If we produce 1, we're going to get $2,000 plus whatever. So, bottom line though is that if we want to do the average between the two endpoints of, let's say, 0 and 2,000, we know it's going to cost $2,000 to produce 0. If we produce 100 of them, it's going to cost $11,000. Okay, so the average rate of change in this particular case would be 11,000 minus 2,000 over 100 minus 0. And if we do that, we're going to get, of course, 9,000 divided by 100. Okay, and that's going to give us $90 per machine. Okay, so the average rate of change is $90 per machine. But what we want to know is what's the instantaneous rate of change for this particular situation, and that's what we call the marginal cost. Okay, the marginal cost is always the derivative of the cost function. Okay, so knowing that if we find the derivative of it, and we find the derivative at a particular point, we can find out how the cost is changing at that point, and it will still be the same units, dollars per machine. Okay. So if I find the derivative, which I did here, I found the derivative using the power rule, and if we find the derivative at 100, okay, we can see that the answer, if we put 100 in here, we're going to get 80. So 20. 100 minus 20 gives us 80, and again, that's in dollars per machine. Okay. So the question is, what is the marginal cost really telling us? Okay. So we're saying that at 100, once we're at a production level of 100, okay, that means that our cost is increasing at a rate of $80 per machine. Okay. So what that can tell us is that if we were to produce another machine, okay, we could expect that the price be about $80 more. Okay, because again, we're growing at a rate of $80 per machine. Okay, so if we're at 100, okay, we should expect that with 101 machines, that our price would be about $80 more than what it was at 100, which remember was 11,000. So we might predict, based on this information, the fact that I'm at 100 and my cost is 11,000, that if I went 101, then my cost would be 11,080. Okay. Now, we do have a cost function in this particular case, and if we look at the cost function, okay, again, our prediction would be 11,080, okay, 11,000 plus 80 more, because every one machine that we produce at that point is yielding us another $80. So if we actually do the cost function, though, we get 101 in there. It turns out to be $11,079.90. So again, it's not exactly 1,080 or 11,080, but it's very close. Okay. So again, that marginal cost, thinking about what that looks like in graph format, okay, if we know the value at 100, okay, and we want the value at 101, okay, if we were to add the slope to it, okay, that would be a run of 1. The rise is 80. If we rise 80, run 1, okay, that would put us at this point, which would for us would be 11,080. Okay, again, the curve is actually a parabola, so it doesn't go on in a linear manner. Okay, so and we should expect that, knowing the nature of a parabola, that it be a little bit lower, okay, than what we would estimate it with the tangent line. Okay, so by doing that, again, we're just taking the tangent line and we're using it to make a prediction of what the next one would be. Okay, so if we're at 100 and it's 11,000, okay, to produce one more machine, the rate being 80, if we were to go up one more to the right, okay, we should expect it to be 80 higher, okay, based on that particular slope. All right. Now, there's one more problem I want to look at here, and that's number 24 on your book problems. Okay, they give us a position function, and with that position function, okay, what we want to decide here is, okay, when is P moving to the left, moving to the right, and standing still? So this is a position function. Okay, when it's moving to the left would be when the derivative of it is negative. So if you look at the derivative being negative, that would be from 2 to 3, the derivative would be negative, and also from 5 to 6, the derivative would be negative. That's where we have a negative slope, okay, of this position function. Right. When it's moving to the right would be when the derivative is positive, okay, and the derivative of this is positive from 0 to 1, and that's it. And then finally, where it's standing still is where the derivative equals 0, which would be the 1 to 2, and also the 3 to 5. Okay. And what we're also going to look at is what would a graph of the velocity look like, and what would a graph of the speed look like? Well, remember from 0 to 1, the velocity is constant. Okay? In fact, if you calculate the slope, it goes up 2 over 1. It's a constant 2. Okay? So anytime that we have line segments as our position function, then the derivative function that we draw, which is the velocity in this case, is always going to be horizontal line segments because the slope does not change. Therefore, the derivative we draw had better be constant. So if you look at the picture that I've drawn, okay, on the first branch here, I went from 0 to 1. Okay, I said that it's the horizontal line segment 2 because that matches up with the slope of the function in the picture. Okay, between 1 and 2 and 3 and 5, we said the slope was 0. So notice the y values of my picture are 0, okay, matching up with the slopes of the original function. If you calculate the slope on your picture between the points x equals 2 and x equals 3, it turns out to be -4, so hence I have a horizontal line segment at -4. And then from 5 to 6, if you go from x equals 5 to x equals 6, the slope is -2, and hence I have a segment here at -2, because -2 values match up with the slopes of the original function, just like we have done so far. Now, keeping in mind that the speed is equal to the absolute value of the velocity, okay, you'll notice how different this graph is. Okay, this does not change because 2 is still 2. These zeros don't change because the absolute value of 0 is 0. But you'll notice that my segments for 2 to 3 and 5 to 6 are above the x-axis because ultimately, if I look at this as the velocity -4, the speed is actually +4, and hence the segment would be above. Okay? Same with this one, the velocity here is -2, the speed would be +2, so we would draw that above also, because this would be a speed graph. If you ever draw a speed graph and you have stuff below, okay, it's not going to be right, because again, speed is always the absolute value of the velocity. Okay? So those are a few different applications that we're going to take a closer look at in this section. So we're going to work on some homework problems, and then from there we'll continue our discussion.